OSPF basically stands for Open Shortest Path First, and it is also the second kind of its own regarding the interior routing protocols. If you want to discuss that, so we are going towards that discussion as well. OSPF divides an autonomous system into areas. So the only thing that is differentiating between this and the earlier protocol is that in this kind of protocol you are going to further divide your autonomous system, that is your AS, into further areas and sub areas, and this is why the purpose of this division is that you will be able to you will be in a better capacity to handle the routing efficiently and in a timely manner. So to that if you have divided the a big network into a small network, so you will be able to handle that very much efficiently. And similarly, if you further divide this kind of autonomous system AS into more further areas, you will be able to handle that areas independently more efficiently. So okay, so what is area? So area is basically a collection of a network or host and different routers all contained within a one autonomous system. You cannot have a same area that includes a different autonomous system. The areas is basically a subset of autonomous system. Your different routers and devices should be connected in a single AS basically. So autonomous system can be divided into different areas, and all networks inside the area must be connected to each other. So this is also an important point, that these different devices should be connected within the same area of the same autonomous system. So routers inside an area basically flood the area with the routing information. Each area has a special router called the area border router, and this will be helping you to summarize the information about the area and send it to the other areas. So we will discuss this inshallah also in detail in the class as well. So, among the area inside an autonomous system, there is a special area called the backbone. You know that the importance of a backbone in a human body. That is why this terminology is given to the same concept over here. So all the areas inside an AS must be connected to the backbone. So you can say that backbone is the main thing, and that is taking the information about all the other devices that is inside that area of the same autonomous system. So the routers inside the backbone are known as basically backbone routers, and the backbone router can be also basically termed as area border router, because this backbone will be assigned, and this will be responsible to communicate with other areas. So an area, the backbone of an area is basically the backbone router, or you can say the area border router. So if the connectivity between backbone and the area is broken, so a virtual link must be created by the administration. So it is the responsibility of the administration to create a virtual link if the backbone is not reachable, or any other device has broken the link towards the backbone. So each area has a different identification code, or you can say area identification code, and the area identification of the backbone is basically zero. You know that the all zeros concept is the same that is applied over here. The major or the name of the, or the identification of the backbone will be basically all zeros. So this is a perfect example. You can see that this was an M1 autonomous system, and it is divided further into different kinds of areas. There are three areas. You can see that area A0, area A1, and area A2. So this area A1 has a backbone router that is basically connected to all the other devices, either directly or indirectly. You can see that and this is basically your router. So this router will be responsible for this router. So the backbone of this area will be this router. Similarly, the backbone of this area will be this area border router. Similarly, the backbone of this area will be this router. This is the area border router, and this is the backbone router. You can see that this backbone router is basically connected to all the other area border routers. So you can see that, and there are two area border routers. One is this and one is this. So this is the backbone that is connected to all of these, and this is the autonomous system boundary router. So you can, and with this router, this whole AS will be connected to the other AS. So let's say there will be another AS, let's say subnet. So this subnet will be connected to another subnet by using this router. So this is basically autonomous system boundary router, and this is your area border routers 1 and 2, and this is your backbone router. This is very much important because you know that if this goes down, so all these area and the devices within this area will be and this AS basically will be gone down as well. So let's talk about the matrices, or you can say the cost that you are going to pay, or this routing protocol basically have to pay. So there are different matrices that basically the administrator decides that what should be the cost or what should be the matrix. So you can say that let's talk about this PF specifically. In OSPF, the metric can be based on the type of service, that what kind of service you want. If you want something like you want a minimum delay, let's say you are playing a multiplayer game, let's say, or you are watching a live streaming, so you do not want to have maximum delay, so you will find a route towards your destination that will provide you the minimum delay. So in that scenarios, the matrix should be the minimum delay. Let's say these are two devices. The one is a destination source and the second one is destination. So this I forgot to tell you about the disadvantage of actually RIP. In RIP protocol, there's a major disadvantage that just came to my mind, that in that protocol you have let's say two paths, the one with the 5 or 6 hops, and the second one is with the 2 hops, let's say, or 3 hops, 1 2 and 3 hops. There are 6 hops, let's say, over here, and there are, let's say, 3 hops. So always this source will decide that he should be going through this path. It will not take any other matrix. Let's say this is of this channel is of, let's say, 100 Mbps. This is a bandwidth of 100 Mbps, and the bandwidth of this channel is, let's say, 200k kilohertz, sorry, kbps. This is the capacity of this channel. So the router will always select this path, and you know that this will cause maximum delay, because this protocol never take any other matrix into account. It only takes the hops into account. So this is the major disadvantage of that protocol. I have just reminded me over here, so that's why I have told you. So let's get back to OSPF. So in OSPF, the matrix is basically the minimum delay and the maximum throughput. You can also select this as well. So let's talk about the minimum delay. Let's say you have 2 different paths, source between the source and destination. So only that path will be selected by this router or source that will provide you the minimum delay. Let's say when you go from this point to destination using this path, it will take, let's say, 1 second. And if you go from this path, it will take, let's say, 2 seconds. So the router that is placed over here, that is responsible to forward the packet, it will always forward the packet to this path, because the time required is minimum. So this is the kind of metric that you are just we just discussed about. The second one is basically maximum throughput. And this again basically is, let's say, this is taken 1 second, but it is the channel is of let's say 100 or 10 Mbps, and this channel is taking 2 seconds, and the bandwidth of the channel is let's say 100 Mbps. So you see that the throughput is basically increased over here. You can transmit much data in this channel, and the delay will obviously the least. If you have this kind of system, the delay will be minimum as well. So this will not be too in this scenario if you increased this kind of bandwidth. So now there will be maximum throughput over here, and the device or the router, this R1, will be always selecting this path if you are given the option of to go for the maximum throughput. So it will choose that path that provides the maximum throughput towards the destination. So a router can have multiple routing tables, and each routing table basically is based on different type of service. So a router, let's say this R1, this will be having two routing tables. One is for the shortest this minimum delay, and the second one is because of as for maximum throughput. So whenever a packet came and it wants a maximum throughput, so it will look the search for the destination in this routing table. And whenever a packet comes and it want to be delivered in the minimum time, so this router will go into this routing table. So a router basically can manage up to more than one routing tables as well, depending upon the cost and depending on the quality of the router as well. We have discussed about different kind of routers in the last class. So if you haven't watched that video, I will recommend you to watch that video at least one time before this lecture. So let's talk about link state routing. So OSPF basically use link state routing to update the routing table within an area. So you know that I have talked about the area. So who will be responsible to update the routing area? So this routing table will be updated within an area. So what is link state routing? So link state routing is a process by which each router shares its knowledge about itself and its neighbor with every other router in the area. So this router will be communicating with every other router, and it will provide all the information about the neighborhood towards all the destinations. So there are three keys for that. The first one is basically it has to share the knowledge about the neighborhood. So each router basically sends the state of its neighborhood to every other router in the area. So the router will be transmitting information about the neighborhood, that in my neighborhood there is R1, R2, R3 and I am R4. So this will provide the information. This R1 or R4 will be providing such information about the whole of the neighborhood. Similarly, this router should be have the capacity to share the information with each and every other router. So each router sends the state of its neighborhood to every other router in the area by flooding. So you know that what is flooding? It is a kind of broadcasting, but in broadcasting there is some kind of difference between the broadcasting and the flooding, and we have discussed that in the class as well. Let's not go into that detail, and if you want to discuss it further, you can watch the previous class discussions actually, in which we have talked about the flooding and the broadcast. So each router basically floods the information about its neighborhood, and sharing when there is a change. So each router will be responsible to basically update or inform others if he sees any change in the neighborhood, or any router let's say gets faulted or has gone down with the power issue. So it will have to update other routers as well, that this router is not in a part of our area on the current state. So the idea behind link state routing is that each router should have the exact same topology of the internet at every moment. So different routers cannot have different topologies. They should have a same topology. They should know about all the details that are basically shared. So each router should be having a updated version of the whole scenario or the whole topology. And you know that what is topology? You have discussed about the topology in the very first class. You see that now we are going to connect different kind of phenomena and concept that we have discussed in the previous classes separately. Now we are going to merge them one by one, and you will be seeing that how this information that we discussed in the previous classes gets involved with each other, and how the actual picture you see is divided into sub pictures that we discussed in the previous classes. So each and every router should have the whole picture of the internet, and the router can calculate the shortest path between itself and each network. So at the end of this information sharing, what will happen? So every router will be able to calculate the shortest path based upon the, let's say, cost, or based upon this delay, or based upon the throughput. Every router will be able to understand that which path is shortest for that. So how to represent internet by a graph? So this is very much interesting. There are four types of links in which you can make a graph for using an internet for using of internet. There are four links you can use for that. In OSPF, a connection is known as a link, and there are four kind of link. The first one is P2P. This is very much important. You guys should be remembering it for a very long time. This is not just for this semester. You will be hearing this P2P, this transit. This P2P is now basically converted to D2D as well, device to device. So this is very much interesting. There is a small difference between D2D and P2P, and it should be, I will really appreciate if you will be giving me this answer. And this is not the scope of this course, this is beyond the scope of this course actually, but if anyone finds me the answer, the difference between this P2P and D2D, this is the bonus mark for him or her as well. So let's see who takes my point and give me a small difference between P2P and D2D, and I will be highly appreciating that. So the other link is basically the transient link, the third link is basically the stop, and the fourth one is mostly used by different devices. We will discuss that one by one now. That is virtual actually. So you can see that there are four types of link: point to point, transient, stub, and virtual. So the point to point is a link which is directly connected to two devices, connect two routers without any host or any router in between. So you see that you have direct connection between two devices or two routers without involving any other host. So this is basically, you can take example of a telephone line or T line, or you can represent different routers are represented by nodes, and this link is represented by bidirectional edge. And usually the metric is basically at the same, usually the same at the two ends. Both these devices should have the same metric actually. This is basically your point to point. So if this metric for this router is, let's say, delay, so similar metric should be for this router as well, if they want their information to be exchanged generally and equally. So metric should be same as well. So this is the example for point to point. The second one is basically transient link, and in this kind of link there are several routers attached to it. Within that transmitter to receiver, data can enter through any of the router and leave through any router. You can see that this is basically a LAN or WAN kind of situation where you are even involving multiple routers within, and this is kind of scenario. You can see that there are multiple devices connected to each other, and this is your source, and this is your designated router. This black one is basically designated router. This is basically this realistic. This is basically the transient network. It's this unrealistic presentation, and this is the realistic presentation for this kind of links. You can see that the links are basically shown over here. The third one is basically a stub. A stub is basically a kind of network, or you can say this link is usually operated or used in a kind of network that is connected to only one router. So data packet enter and leave through only this one router. So you can see that this kind of network is basically known as this link is basically known as stub link, in which there is only one router. And if you remember in the last slide, this last lecture 7A, first part of the 7th lecture, we have discussed about a kind of example in which the router F was basically connected to only one router, that was A. So in that example, you have seen the priority table that all these entries for this router table for this F was going through A. So this is the same reason all these devices are connected to a single router. All these devices that are connected through this internet will be connected through this router. So this kind of links is basically known as stub link. And the last one is basically the virtual link, when it is used when the link between two routers is broken. So the administrator, this is the responsibility for the administrator to create a virtual path between two or different users so that they can have their communication. So this virtual link is basically dynamic link, and this is not fixed. Basically, you can replace it with another virtual link as well. So this kind of this is an example of internet. You can see that internet is a form of network in which all these links exist at the same time. So you cannot have internet or any network with only this or only this or only this. Internet is basically a combination of all of these links. And this is the graphical representation of an internet. You can see that all these links are connected via bidirectional graph, which was basically point to point. You see that this is point to point, this is not point to point, this is point to point, this is point to point, even this is point to point, this is point to point, point to point, point to point, it is also point to point, this is not point to point, this is not point to point. So these are all different kinds of representation of graphical representation actually of the internet. So that's for today's class. There are much more discussion to be that should be going to be held in the class as well. So I will highly recommend if you join the class on time, and if you bring some good questions with me with yourself. You see that this is not the only discussion that is going to help you regarding these topics. There is a lot of information, and there is a lot of discussion to be needed for this kind of protocols, because there can be multiple dimensions to understand one single protocol, but due to the limitation of time, this is humanly impossible to discuss all the scenarios and all the dimensions of a single routing protocol in one class of 20 or 30 minutes. So I will highly appreciate if you bring some good questions with yourself, because you know that the more you ask, the more you learn. That's all for today. I'll see you in the class. Thank you very much. Allah Hafiz.